My name's Eric Rosenfeld. I'm one of the interns of the Spartan Superway, and I've been working on the solar team for about 4 months now. And today I'll be discussing the solar installation for an automated transit network. So there's 4 main things I want to talk to you about today. The first is why the Spartan Superway is so significant in this generation. The next would be the overall objectives of the solar team, which will lead into the bulk of the presentation, which is the overall progress of those objectives. And lastly, I want to conclude on the next steps in future work. So one reason the Spartan Superway is so significant in this generation, it is revolutionizing energy users and sources. So as you can see, transportation is the second largest energy user, and the oil industry is by far the largest energy source. And these are 2 industries the Spartan Superway is especially confronting. As we're demonstrating, we can do this transportation easier, cleaner, and more cost-effective. As probably many of you know, the CO2 emissions have been drastically increasing in our atmosphere. As you can see, this is a Keeling scale that shows from 1958 to 2016 the exponential growth of CO2. Actually, just recently, on September 18th, we found the CO2 concentration was 401 parts per million. Now, this is some of the most concentrated CO2 emissions we've ever seen on planet Earth. And so the Spartan Superway aims to give solutions to these problems. Another issue the Spartan Superway offers solutions to is the safety of transportation. So in 2016 alone, 25 million people were injured, 900,000 killed, and $361 billion was spent on traffic accidents alone. I checked that number this morning, it's $369 billion. To put that in perspective, $361 billion would pay for 20,800 full installations of the Spartan Superway. And to emphasize this a little bit more, if the Spartan Superway was the only method of transportation in 2016, we'd have statistics that look a lot more like this: 0 injured, 0 killed, 0 spent, utilizing everything. So there are 5 main objectives the solar team had when designing the solar installation. One was semi-automated installation and maintenance. The next was to determine the consumption of each one of our pods, as well as the necessary production of panels. We also want to make our system adaptive, so we can use it in different regions and different locations. And last but not least, we want our system to be sustainable. It needs to run 24 hours a day, 7 days a week, 365 days a year. So one of the first steps was to understand our location and constraints. As you can see to the right, this is the San José State University and where we plan to install our first initial network. And this initial network has 4.4 kilometers long, around 3 to 5 meters wide, with a constraint of 43,000 to 57,000 meters squared. It's very crucial to keep these in mind when we're designing our solar installation, as we have to obey by all these constraints. So the next step was to determine how many pods we needed in our location. So we took data from the parts and shuttle rides of the city of San Jose. And we computed 70%, which gave us a number of rides over a 24-hour period, averaged in an annual year. And we took 70% of the RMS value, which was 44 pods, and knowing we had a 3-track system, we could easily assume 88 pods. It's important to note we took 70% of the RMS value because a recent study by Aerospace Corporation said if you exceed the system capacity by the slot capacity by 70%, you create a lot of congestion in your system. There's an error.
No, that is my own.
Update this, probably.
I'm stopping the clock.
So you were here.
Yeah, one more.
The next one.
Yeah.
There should be an image here. Or what?
Oh, there we go. That works.
Okay, this.
So the next step, as we found out how many pods we need, the next step is to determine an equation so we can find the general consumption of our pods. We use Professor Anderson of Minnesota's equation, some of you may be familiar with, that accounted for 4 main parameters of consumption: deceleration, air resistance, rolling resistance, and auxiliary power. This was the main equation we used to determine the general consumption of our vehicles. The next step was to determine the coefficients of each one of our parameters. So we ran multiple simulations and computed multiple material calculations, and we determined that air drag, rolling resistance, and auxiliary power were the three main consumptions. Since auxiliary power was mainly user dependent, we decided to put more effort into optimizing the air resistance and rolling resistance. The next step was to determine the losses from local conditions. So we used system advisor model that some of you may be familiar with, that accounted for system shading, soiling, and system electrical losses. And we determined we need around 10.4 million kilowatt hours annually to run 88 pods. And converting this to how many kilowatt hours we're spending per day on each pod and how many miles each pod is going per day, we're relatively getting around 80 miles per gallon, which is very significant. And actually converting this into kilowatt hours per mile, we're getting a more efficient kilowatt hours per mile than the Tesla currently. So once we know around how many our yearly consumption, we need to determine how many panels we need. So the next step was again to use the system advisor model, in which we assumed a Sun Edison panel at 360 watts and at 18.41% efficiency. And system advisor model said we need around 19,600 panels with a required area of 38,300 meters squared. And as some of you may notice, this is able to be implemented in the constraints of our system. So we do plan on installing a surplus capacity of solar panels, and there's three main reasons for this. One, certain times of the day and even certain times of the month, you're not generating as much. So we want to utilize those peak hours as much as possible. Another reason is the payback expensive can be 30 years. So having a higher installed capacity reduces the payback expensive drastically, could be by 10 years. And last but not least, this is a graphical image with small squares in each one of the countries that represent the amount of area of solar panels needed to power the entire country of solar energy. And this is something we're aiming towards. It's a lot of area, but I mean, if we're able to implement the Spartan Superway all throughout California, I posit that we can meet that area in the US alone. And if we're able to move around the world, we're able to implement these areas.
I'm going to stop you guys. You're basically saying that putting in solar panels on pods, you provide enough energy for the whole world.
No, installing a surplus capacity.
Yeah.
So after we're able to power the pods, we install more panels on our system, so we have more area.
And the total energy output of all that, is that square? Is that what you're saying?
No, I mean, if we're able to move across the US alone, I mean, and able to install a surplus capacity in each one of our systems, we may be able to meet that area.
Okay,
so it would require around 800,000 installations of the Spartan Superway.
Right. Thank you.
Okay. So storage is a huge issue. So we plan on using a grid system. Essentially, the solar panels will be able to power our pods whenever they're producing an efficient amount of energy. And in the case that they aren't producing efficient amount of energy, we will unload from the grid and power our pods. Here's a basic electrical diagram. As you can see through the blue lines, we will be powering the pod when we're producing enough energy from our panels. In the case we're producing more energy than needed, we'll be able to sell to the grid system. And in the circumstance that we're not producing as much as needed, we'll be able to unload from the grid system and power our pod system. So semi-automated installation and maintenance is crucial for the Spartan Superway, as these pods will be moving 24 hours a day, 7 days a week, 365 days a year. And we need to be able to fix corrupted solar panels whenever required. And one way to do this, one option was to utilize a robot. And to the right is a local group called Britmore Group that developed a robot that can automatically set down a solar panel. And we think about implementing this in our intermediate track, maybe with an added mechanism that it would be able to twist a cam lock, and with a sprocket and chain it will lock everything up. We have other designs on the way, like pneumatics, semi-automatic coupling systems, and regular coupling systems. Our next goal was to utilize the racking system on the track itself, and to do this, you can see the left rack will be able to use the support beams, and the right track will be able to use the ribs on top of the rack itself. And this will save a lot of cost and a lot of time when installing. Also, we need a blind connecting maximizer. For those that don't know what a maximizer is, it essentially bypasses a corrupt solar cell. And we had an engineer in Brazil that made a design concept that had two connecting mechanisms, that had two conductive couplers, copper pieces, that were simply connected by a wire through this maximizer. There's other design concepts underway at this moment. So there's still a lot of future work we have with the Spartan Superway. One is we want to improve the Podcar design. As you probably noticed, air resistance was a large factor, and reducing air resistance drastically reduces the kilowatt hours consumption per year. We also want to do a financial analysis. So having optimizations of different tracking systems and different actuators may be cost effective depending on the price of the actuators. So we would like to do an analysis on that. We also want to implement a full-scale test track so we can see any possible areas or see any possible improvements of our system. And last but not least, we want to design a racking system, solidify a design for the racking system for the solar panels. And that will be able to semi-automatically install and semi-automatically be maintained.
2 minutes.
I'm done.
Okay.